Hello everyone, we're the team Teletubbies. Welcome to our presentation. This presentation will be divided into following parts, namely challenges, methods analysis, methods comparison, and future improvements. Firstly, given the contest environment, we have identified the following challenges. The game has a 1-second decision window, therefore methods must be able to compute a decision within 1 second. The game can be running on different maps, which means methods must be generalized enough to work on different maps. We have unpredictable opponents, which means methods must consider opponents' behavior very well. With that being said, A-star and approximate Q-learning are selected as they are computationally efficient and highly general. As for Q-learning, we focus more on feature selection, as we didn't have much time to train and experiment with weights. Now I'll talk about A-star. In our implementation, we use avoid ghost heuristic and search through heuristic together with A-star algorithm to find a path to ghosts. Ghosts are defined by different search problems, which are manipulated by hard-coded decision trees. Therefore, the major difference between an attacker and a defender is the decision tree. Now I'll demo some interesting features. Here, the orange ghost is our defender. When he can sense a Pacman, it is an invader problem, in which he will chase the invader. When invader has been eaten, and there is no invader, this is a search-through problem. He will enter the opponent's territory to eat beans, and when he sends a ghost, this is a return-home problem, and he shall return. Likewise, the orange is our defender. When he sends a Pacman, this is an invader problem, in which he will chase the Pacman. The problem will change when the Pacman eats a capsule. This is now a keep distance problem, in which the defender will keep distance of 2 to the Pacman. This feature can distract the Pacman and also wait for scare time to end and start chasing.
Then we will talk about the approximate Q-learning agent. This is how the Q-learning tables look like. Each grid has 4 dimensions: north, south, east, and west. At each step, we update the Q values using the following function, where alpha is the learning rate, QSA is the old Q value, R is the reward, gamma is the discount factor, and argmax Q is the estimate of optimal future value. That is equivalent to the definition of Q function Python basic math. In order to obtain the optimal future value, we evaluate the approximate Q value as the multiplication of features and weights. 4 features are used: distance to the nearest food, distance to the nearest opponent, distance to the start point, and distance to the nearest capsule. The weight vector has the same length as the feature vector. The weights indicate how important the features are. We use a different weight vector for different conditions. For example, we would use 1001 for seeking food and capsules, but ignores enemies. Compared with A-star algorithm, the Q-learning method is more generalized, which means the method will work for most situations. A decision tree is not necessary. The second advantage is that we would expect that the Q-learning agent will have better and better performance through training, but the performance of A-star agent will not change over time. There are some disadvantages of Q-learning agents. First, the Q-learning agent takes a longer time to train, and the ongoing time complexity is larger than the A-star agent. Second is that the Q-learning agent does not have quick response to danger, but the A-star agent will immediately react to enemy ghosts. In this demo, the A-star agent detects that the enemy ghosts are approaching, so it goes back home immediately. However, in this one, the Q-learning agent failed to get back. It keeps on eating food dots even when the enemy ghosts are very close. The reason for that is the Q values are changed gradually, so even in danger, the food grids still have larger Q value than the grids that goes back home. After several steps, the agent will still choose to go back, but sometimes it's too late. Some future improvements of Q-learning include: first, we could use a more complex evaluation function. We could have more features indicating more complex situations of our agent. For example, we could use the number of foods that is currently carrying on our agent as a new feature. Number 2, instead of hard-coding the hyperparameters, we could use stochastic gradient descent or grid search to find the optimal hyperparameters, alpha and gamma. Also, we could try to train the feature weights based on past events. Number 3, we could include reward shaping method. For example, we could say that eating a capsule would generally be better than eating a food dot. So we will add the reward shaping function, which is the Manhattan distance to the nearest capsule. Game theory method could improve the performance of the A-star decision tree. We can find all possible combinations of the actions, then we use min-max tree method to evaluate the average reward of each one and choose the action that with the greatest average reward. Also, we could have a better scan map method. Now we only care about whether the food is safe or not when scanning the map. We could also evaluate the weight of each food's reward when scanning and use heuristics to find the food with best reward. Also, we could give different weights to capsules.